All right, recording is rolling. So it is Tuesday, October 18th. So my plan is to take today, tomorrow, and solve a bunch of problems with you guys. So you guys get to break out the calculators. I'm gonna solve some stuff. You guys remember you have here. Yesterday we did a Kahoot with these 20 conceptual questions. You guys got all those answers. And when I eventually get you guys the footage, which is coming up here pretty soon, but the next few days, then a lot of the questions are straight off that. But printed on the other side of the same page are all these like algebra-based questions. Okay. Right, so that is what we're gonna go over class today. Right now, for context, right, we just had a fire drill. We're like 20 minutes into class we would normally have. So class was about half the length it usually is, but that's right. We'll just do as many as we can. Right, so you guys have different versions of this page. I print out different versions, right? So what we got here? Let me zoom in and give you guys a quick review. Right, there's all the formulas you guys need right here. There's universal gravitation, right? So two masses, capital M and lowercase m, some number of kilograms each, they will gravitationally attract. Okay? And that force is proportional to each one of those masses, but also inversely proportional to the square of the distance between them. That's what divided by r squared is, right? So r could be the distance, and r is a good value, a good variable for distance because a lot of these cases are orbiting, right? If you have some like orbital radius, right? It doesn't necessarily have to be orbiting, but it could be. Okay? One right below that. So if you take a force and divide by that small m, this could represent gravity free fall at the surface of a planet. Right? If you know universal gravity constant, the mass of the planet, and the radial size of the planet, boom, 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 pop it in. And for Earth, for example, those numbers should come out to like 9.8 meters per second squared. Right? If you know the mass of the Earth and the size of the Earth. Um, Potential energy, we haven't actually even talked about that yet. So we'll do that in the future. Okay. Here's the universal gravity constant, a tiny, tiny, tiny number at 6.67 times 10 to the negative 11. So that's 0.000, just a string of zeros before you get to the 667, right? Follow the scientific notation. Okay. Nobody knows why this number is what it is, but it's been empirically measured to be that. Okay. We got Kepler's third law of planetary motion, which you can actually derive from all the Newtonian stuff that came afterwards in history, but it's kind of nice to have, right? So this relates the time period of a planet around a star to its distance from that star, right? Or you could even do like satellites orbiting the Earth. So it could be like low Earth orbit versus the moon versus like geosynchronous orbit. Right? So a bunch of satellites orbiting something, right? A bunch of planets orbiting a star. Right? You can figure out the relationship between how far away they are and how much time it takes to go around. Okay? Now, escape speed is something well, I can technically prove this using conservation of energy, which we haven't quite got to yet in the class. Right? But escape speed, if you look at it, it looks a lot like orbital speed, which I think it did derive with you guys. Right? It's just that if you slip a 2 underneath that square root, okay, so you need some speed to stay in orbit, which you guys know for Earth is about 8,000 meters per second. I think we calculate like 7,900 something meters per second, right, to stay in orbit around the Earth. Right? And then if you slip a 2 under there, right, multiply that square root of 2, you can ultimately reach a speed that's fast enough to break away from the planet. Right? You can go so fast you can like fly away forever. Right? So that's going to be a future topic, but you guys have it printed there. And we'll apply it too. Okay. And so first question, what is the gravitational force between, and I picked two objects. So the paper I have right here on the projection says the sun and Saturn, right? There's some gravitational force between the sun and Saturn, for example, right? You might have this paper, you probably have a different paper, but that's okay because I got lots of different versions and I'm gonna switch through as we go along here. Right, so this is gonna be, the setup is pretty straightforward. It's just gravitational force is G M M over R squared. You know, I should have drawn a picture first. Let me do that. Okay. So here could be the sun, right? And here is Saturn. Right? It's got some rings, the whole deal, right? Right? And the sun, I'm going to call capital M, right? Well, that could represent its mass, and then lowercase m could represent the mass of Saturn, right? And there's some center to center distance between those two, right? And I'll call that distance lowercase r. Okay. Okay. Now, Saturn is orbiting the sun. You guys know, since I started talking about Kepler, that the orbit is not exactly circular, it's actually elliptical. but it's kind of close to a circle. So we're going to say this R, even though it varies a little bit. Right? We're just take kind of the average value, run with that. So I'm going to write that formula that I wrote. The gravitational force between the two. Right? Remember, this is causing a centripetal force on Saturn, but it's the gravitational force. Here's universal gravitation. Universal gravitational constant times the two masses multiplied together, divide by the distance between them squared. Okay. Okay, so if I gave you each of those numbers, all you have to do is plug the numbers in. But part of the trick this week is making sure you can use the calculator correctly, because you have to figure out where do the parentheses go. We're grouping stuff together with scientific notation. Okay, so that's part of the trick. It knows that just based on teaching this class so many years, right? That's part of the trick is that can you plug the numbers correctly into the calculator? Okay. So it's easier to write though. You can just pop the numbers into the square. So G, that's the universal gravity constant, 6.67 times 10 to the negative 11. Okay. Now it has some units attached to it. Here's what I do. I'm going to take all the units and just bring them out to the outside. This force would be measured in newtons. So this is going to be some number of newtons by the time you consolidate all the units. Okay. The mass of the sun, that's 1.99 times 10 to the 30. Okay. And that's kilograms. If I wrote the unit kilograms, okay. Here's 1 kilogram. So the sun's about 10 to the 30 of those. Okay. Of course, took care of the units already. Okay. The mass of Saturn. Okay. Now this one I have to look up. All right. So on the page it says 5.68 times 10 to the 26. 5.68 times 10 to the 26. And that's kilograms. Okay. You might remember for Earth is like 5.97 times 10 to the 24. 10 to the 24. And Saturn is like 10 to the 26. Guys, how many times more massive is Saturn compared to the Earth? It's 5 and 5 are about the same anyway. So what is 10 to the 26 compared to the 10 to the 24? How many times bigger is that? This is a side question, but side questions are fun in physics, right? You can pause and say, wait, well, what does this number really mean? Let's try this out. What is 10 to the power of 26, close parenthesis, divided by, open parenthesis, 10 to the 24? Because Saturn's 5 point something, Earth is 5 point something, so that number's kind of a wash, pretty close to. Okay. So I really care about the order of magnitude. Okay. Anybody have a guess before I hit enter? 10 to the 26 compared to 10 to the 24? Isn't the exponent rule like you subtract the exponents? So what is 26 minus 24? It's 2, right? And it's 10 to that power. So guys, what is 10 to the power of 2? That's 100, right? 10 squared is 100. Oh, that's 100. Right. So Saturn is about 100 times the mass of Earth. Whoa, isn't that interesting? Okay. And then R. Now this R is the distance from the sun to Saturn. I have to look that number at 1.4 times 10 to the 12 meters. 1.4 times 10 to the 12, that's meters. That's being squared. Okay. Now, because these numbers are all in base SI units, right? I mean, it's going to consolidate to newtons, took care of that already. Okay, so now time to plug this into the calculator. So here's really good practice, right? Now, your quiz, when I initially get it to you guys in the next few days, again, most of the questions are conceptual, but there are a few calculation type questions. So make sure that you can do this. I got open parenthesis, 6.67 times 10 to the power of, and then you have to choose this negative key at the bottom of the calculator. If you have a different model calculator, then figure out how your calculator works. But if you're using this one right here, there's 2 subtract signs, but you have to choose the negative sign at the bottom. Okay. If you choose this one, it doesn't work. Okay. Negative 11, right? Close parenthesis, open parenthesis. This model calculator automatically multiplies. Not all calculators do, so be careful about that too. 1.99 times 10 to the power of 30. That's kilograms. Close parenthesis, open parenthesis. 5.68 times 10 to the 26. Close. Okay. Then divide by, open parenthesis, 1.40 times 10 to the power of 12. Close square. Don't forget to square that radius down, right? Okay. So got everything grouped like it needs to be. Everything's in the right spot. Got all scientific notation. Got the negatives where they need to go. So if you did that all correctly, you should get the right answer. So I'm getting, the number on my screen is showing 3.8465, around like 3.85. Okay. And then times 10 to the 22. And of course, this would be number of newtons. Okay. So just make sure that is answer choice. 3.85. Yep, it's right there. Bam. That's exactly what that says. So we're good. Okay. That is the force on Saturn, like the total force. How many newtons? Okay, good. All right. Number two, a satellite orbiting Saturn has some given mass. What should be its linear speed to stay in a circular orbit? So let's say it's pretty close to the surface of the planet Saturn, like it's just above the clouds. Okay. So number two, you know what I want to do? Yeah, I'll keep the same page. I'll switch out a different version later. Okay. So let's keep Saturn. Okay. So I got Saturn. Right, it's got its rings, the whole deal. Right. Let's say we send a space probe to Saturn. All right, we're going to send it just above the clouds. So here's our space probe. Okay. And we're going to keep it in orbit about this planet. It's going around, right, like inside the rings, right? Okay. And I'm saying that whole setup because now I can use the radius of the planet itself as also the orbital radius, right? That they'll call it R, like a fixed R. Okay. Now, orbital speed. I did print you guys that formula pretty big right here. Okay. This paper has been through different iterations over the years. Originally, I had you guys derive it from scratch. So, I'll do both. I'll derive it from scratch, show you remind you guys where this comes from, and then we'll just go ahead and apply this. So, there is a force from the planet that has a weight, right? That's pulling it in. And if you start from rest, it would just free fall, plummet straight into the clouds, straight to the planet. But if you give it a tangential speed, it's like v speed, that's going around, that's like into the paper, right? If it's going fast enough, and that's what we're trying to calculate, the orbital speed, okay, then it's like falling around the planet. So that force that's pulling is acting as the centripetal force. And I know what centripetal force is. This is the answer to your guys' lab. You guys remember the Play-Doh canisters and the whole deal? Right. So that's centripetal force. Oh, actually, I got that paper right here. Right, just remind you guys, if you need the visual. You guys remember doing that lab right there? Right. This was the answer to that lab. That's for centripetal force. That's what centripetal force is equal to. But that centripetal force is provided by the gravity force. Now here's universal gravity force, Gmm over r squared. Right. The simplified version is just m times g, lowercase g, but right, here's like the full version. Right. So, right, and we're trying to solve for what is this v? Right. That's the question. Now, there's some simplification. You guys see one of the r's is going to cancel. If you cross multiply to r, that cancels, and this partially cancels, right? So now it's r to the power of 1. Right? And also this little m cancels. Guys, what does the little m mean in this context? The mass of what? Right? Like, I know the big M is Saturn. Right? Here's capital M. The big M is Saturn. Isn't the little m the mass of the satellite right here? Right? And that cancels out. Okay? So it turns out it doesn't matter how massive the satellite is, right? As long as it's really small compared to the whole planet, which it will be, okay? Needs the same orbital speed. Okay? So solve for this v, there's only one algebra step. The one algebra step is how do you undo a square? Take the square root gm on r, okay? And that is exactly what's printed right here. Look at that. The orbital is square root gm on r. Like I said, right? So that's where it comes from. Okay. It comes from, I should have done a step before this. It should have said centripetal force is provided by the gravity force. Okay, but that just leads straight into this and then this. All right. So the orbital is, I got a big old square root. Oh, and remember what I was meant to say on the last one too, is if plugging this all into the calculator in one go is a bit complicated, you could break this down to smaller steps. So you could say, well, you multiply some of this stuff and then get an answer and then take the square root out of the fact. But that's perfectly fine. You can do that. Okay. But I'm taking a square root of a bunch of stuff. This is going to come out to some number of meters per second. I'll do what I did before. I'll just take the unit out on the outside. 6.67 times 10 to the negative 11 and a bunch of weird units, but yeah, took care of the units. The mass of Saturn, this number is 5.68 times 10 to the 26. That's kilograms, but again, took care of the units. So, and the radial size of Saturn is 6.03 times 10 to the 7 meters. 6.03 times 10 to the 7, that's meters, right? Okay, so I got everything in my basis units. Yeah, go ahead. Oh, yeah, go ahead. All right. Okay, so, yeah, if you want to do all the stuff inside first to get an answer and take square root later, we can do that. But if you want to do it all in one go, I can do this. You do square root. Okay. Now, here's a tricky thing. Okay. when you're applying the square root, see how this calculator automatically opens a parenthesis? Okay. So every calculator is different, but this one does that. Okay. As soon as that parenthesis closes, it stops square rooting. Okay. And then it'll just like continue to multiply after that. Okay. But I want all my numbers to be underneath the radical. Right? I want everything to be square rooted. So to avoid like closing the square root too early, I can just open up a ridiculous number of parentheses. Right? This is just a little calculator trick with this model. Okay? And then for sure, everything's going to be square rooted. So it's going to go 6.67 times 10 to the negative 11, close open. 5.68 times 10 to the 26, close divide by open. 6.03 times 10 to the 7. Okay. Okay. Guys, okay? And this comes out to, ooh, that is a big orbital speed. It's like 25,000 some meters per second. Okay. Okay, so yeah, that looks like this one here. 2.51 times 10 to the 4. Okay. You know what? Let me show you guys 3 different ways to express this number. It's this many meters per second right now. Right? You could also say 25 point something kilometers per second. You could do that. Right? In scientific notation, right, let me go back to the original version. There's an implied decimal right here. Go 1, 2, 3, 4. 4 decimal places to move it to the units place. I can go 2.5066 to 2.51. Got 3 sig figs. Looks like I do over and over. You know that much precision. Okay. Then to restore the decimal place, well, that's 4 places, so 10 to the power of 4. That brings it back to here. Okay. And that's meters per second. Okay. And that's what this answer looks like right here. Now, I want to definitely give you guys all the different versions of this because I know I've printed different type papers. And some of you guys, I think I actually did like this with it, did kilometers per second. So some of you guys have kilometers per second. Some of you guys have scientific notation meters per second. Right? But regardless of what you have, now you can field any version that you have. You guys can do this? Right? You guys remember for Earth, the orbital speed was like about 8,000 meters per second. And for Saturn, Saturn looks like it has to go more than 3 times as fast. You guys see that? Okay. Because Saturn is like so massive, right? It's a huge planet, second biggest planet in our solar system. All right, guys good? All right, now number 3. Right, now number 3 is one of these proportion type questions. Taking a look at the inverse square law. Okay. Let me do all the number 3s with you guys. Okay. So it says 2 objects float in space some distance from each other. And we're going to take that distance and we're going to change it by some factor. Right? And every paper says a different factor. Okay? How does the force between the objects change? So we got these 2 objects, some mass, whatever. Okay? There's some distance between them. Okay? Now the distance we're going to focus on. Okay? I'll call that distance R. Right? And I know that the force of attraction between these 2 guys, because they're pulling on each other, force, equal and opposite forces. They might be different masses, but it's the same force. What's that force equal to? Well, here's GMM over R squared, right? You guys know that. We've been applying that today. Okay? But this is not a plug and chug question. This is not, I'm going to give you some numbers and you can calculate it. What we've done so far was that, but this is different. This is going to be, I care about proportional relationship between this F and this R, right? This force and this separation distance. So I'm going to make a partial equation. I'm going to set up proportionality. Force is proportional to 1 over R squared, right? Okay. And that by itself could answer everybody's number 3. Okay. So let me see the paper I have right in front of me, and then we'll do the different versions of this. Okay. So the paper in front of me says shrinks to 1/4 of its former distance. Right? So if I take this distance and I shrink it to 1/4 of the original distance, R turns into R over 4. Right? First of all, is the force of gravity between them getting stronger or weaker? If they're really close to each other, is it really strong or really weak? I think it's really strong because see, if they were really far away from each other, that'd be a really weak force, right? What it's consistent with is, I think yesterday I showed you guys this graph, right? Like, so it's like this rocket leaves this planet. Hey, this could be 2 masses, right? Mass, right? And as you go further away, remember the force gets less and less and less. This is as long as you're outside the planet, right? It's going to fall. Hey, inverse square law, right? There's graphically what this looks like. Right? So back to here, that's what that looks like. So So I know the force is going to increase, but how much does it increase by? Well, it's 1 over the distance squared. So let's call this the original force. Force is, well, do that right, GMM over R. Here, I'm just going to cut this. Let's say GMM comes out to like one unit of something. Right? So just to keep it simple, 1 unit of something over R squared. I'll call this the original force. Okay. Now the new force is going to be 1 over a quarter of R squared, right? All right, guys, what is 1/4 squared? Is that like 1/16? Right? If you have a quarter of a quarter, right? I'll tell you, just in case you guys don't see that. Suppose you order a pizza, right? And you have a quarter of a pizza. That'd be like this wedge right here. That'd be a quarter of a pizza, right? Okay. But then what if you had a quarter of that quarter? When you have to break this into force, that would be like this little wedge right here. Right? You guys got dark wedge? Isn't that a quarter of a quarter? Right? Which is like 1/16 of the whole pizza. Okay. So F nu is 1 over 1/16 R squared. Right? But hey, see how there's a fraction within a fraction? Right? You guys see that too? Right. How about this? If you have, let's review fractions. Suppose you have A divided by B over C, right? Isn't that the same thing as A times C over B? You guys remember that? Right? If you have a something divided by a fraction, you can take the denominator fraction and flip and multiply it. You guys remember that from math class? Right? And we're going to do the same thing over here, right? So if you have 1 divided by a 16, is that the same thing as multiplying by 16? Okay. So isn't F nu equal to 16 times 1 over R squared? That's the same thing, right? But 1 over R squared was the original force. That's that. So the new force is 16 times the old force. Okay. Now, even before I started plugging and chugging, I knew that the force was going to increase. We talked about that. We said if they're getting close together, the force is going to go up. They go away, it's going to get weaker. But if they get closer, it's going to increase. Okay. How much does it increase? 16 times. Right. So if the distance gets cut to a fourth, the force goes up by a factor of 16 because of the inverse square law. Okay. So there you go. So 16 times the force. Okay. Now, some of you guys have that paper, but again, there are lots of different versions floating around. So let's shuffle through here. I got one that says it shrinks to 1/3 of its former distance. Let's see what that would be. So if the old force, again, was just 1 over R squared, let's say GMM comes out to like 1 unit of something crazy. Okay. Then the new force would be, let's see, it shrinks to 1/3 of its former distance, right? There's 1/3 of the original distance, right? And that's all being squared, which is like 1 over 1/9 R squared. 1 divided by 9 is 9. So this is 9 times 1 over R squared. And 1 over R squared was the original force. So the new force is 9 times the old force. Right? Right? That's it. Right? So 1/3 of the distance is 9 times the force. If you don't have that paper, maybe you have this paper. The force is, the distance is cut in half. So like half the distance. Let's try that. So F, say old is 1 over R squared. F new, 1 over, okay, so now we got half the original distance, and that's being squared. Okay, so that's, say, 1 over a quarter of R squared, which is 4 times 1 over R squared. 4 times the old force. Okay, so if you have half the distance, you have 4 times the force. Okay, now those 3 examples we just did are all decreasing the distance between the two, which is going to increase the force. Okay, let's look at some more examples. Okay, now the ones I haven't done yet that we're about to do are, what if you increase the distance between the two? Well, if you increase the distance, then isn't it true that the force would be getting weaker? Okay. So let's do F old is 1 over R squared, okay, or proportional to that. Okay. So F nu is, right? So quadruples, right? 4 times the distance for our quantity squared. F nu equals, let's see, 4 squared is 16, right? This is this, right? But the 16 is in the denominator now. Right? So it's 1/16 of the old force, right? So if you have 4 times the distance, you have a 16th of the old force. Okay, inverse square law, inverse square law. Okay? There's 2 more examples. Let's do 2 more examples here. Suppose the distance triples between the 2 objects, triples. I could just do F nu equals 1/3r quantity squared, which should be 1/9 over r squared. Yeah. Which is 1/9 of the old force. Okay. And so if you get 3 times the distance, 1/9 of the force, inverse square law. Okay. And there's one more they could possibly have. Okay. And that's, what if the distance doubles? Right, the distance doubles. Okay. So again, the force should be going down because of inverse square law. The force is going down, but let's see how much here. Okay, so F old, one of r squared. All right, so F nu is 1/2r quantity squared. Here, it's going to end up being a 4. All right, so that is a nice short class. I will see you guys tomorrow. We'll solve some more of these problems. All right, you guys enjoy the rest of your day.